Good day, Dr. Norila and everyone. We are from Group 15. Today, we are going to present our Milestone 3 project. This is our schematic diagram of the 4-bit ripple carrier adder. It is obtained from Milestone 1 and can be used directly without modification and simulation as it is entirely reusable. This is the BSF file of this ripple carrier adder. Next, this is the cell unit of an accumulator and is designed as shown in this schematic diagram. And after that, by combining these 4 cells, an accumulator is built. After that, we set it as the top level entity and combine this one. Then we open this simulation waveform editor and we run functional simulation to test the function of this built accumulator. In this simulation waveform editor, it can be seen that the value of D is routed to the output Q for every rising edge of clock when the clear is low. Next, when the Q is clear for every rising edge of clock when clear is high. Next, I would like to show the schematic diagram of the Knight Rider. The Knight Rider design is obtained from Milestone 2. However, the Knight Rider design is modified to meet the requirements. In our modified design, the input pin clock enable of LPM counter is added to enable or disable the lights so that the LEDs run only when the input is high. Next, the O9 output pin from 7442 chip is connected to the done output signal through a NOT gate to indicate the end of a cycle. A NOT gate is required to convert output low to output high when the cycle is completed. An OR gate is also connected to the enable input pin to allow the Q reset at the next clock for every time this S clear is high. Next, I set it as a top entity. Then I run and compile this design. After that, I open this simulation waveform editor. I input all the signal here. Then I run the functional simulation. As you can see, when the enable pin is low, there is no effect on the output. All the LED will light up, but it stops at the LED A, which is causing LED A does not light up. And when the enable pin is high, the LED start to show the Knight Rider pattern. As you can see, every time when the circuit approaches the rising edge of the clock and the LEDs start to show the Knight Rider pattern, the LED does not light up, change from the LED A to LED F and then return to LED B. After that, when a cycle is completed, output high is sent to the done LED to indicate the completion of a cycle. And this depicts the success of our Knight Rider design. This is the schematic diagram of our design pre-scanner. As you can see that bit 25 and bit 18 output are selected as output clock signal because they can generate 1 Hz and 100 Hz clock signal. After that, I set it as top level entity and I compile it.
From the weighing machine, we have the comparator, and this is how we design our comparator. This is a 4-bit combination comparator which has 2 inputs. The input A is obtained from the accumulator, and the input B we set as 11. This is because we want to obtain a high output when the input is greater than 11. And this is our simulation. The A is from the accumulator and B is set as 11, which is B in hexadecimal. Then we start our simulation. And this is our simulation output wavefront. And this can be called a success because we obtain a high output when the input is greater than 11, which is B. Inside the BCD converter, we have to design a 8x3 adder CADD3 in order to produce a 2-digit BCD. And this is our design for CADD3, and that is the input B and also the output D. Let me start the compilation. After compilation was successful, let me go to the simulation. And this is the simulation output wavefront of CADD3. After we complete the CADD3, we connect the 1 bit of the output to the NOT gate, and then we connect the NOT gate to 2 outputs of the BCD converter. The 3 bits of the output of CADD3 we will connect to the 7447 BCD to 7-segment decoder, and all the output of the 7447 we will connect to the output of the BCD converter. And all these output later we will assign the pin. So now we can start to do the compilation. After the full compilation was successful, we can do our simulation. And then this is the simulation. The input is B. Let me start the simulation. So this is our simulation output wavefront of BCD converter.
Hello, this is Chen, and I'll talk about the input filter, selector, and the overall design of the vending machine. Okay, this is the input filter that we designed, and the idea of having this input filter is to avoid the misreading from the push button due to the amount of the time of pressing the push button from a human. So we used 2D flip-flop and we connected it in a series with a common clock, and we use the concept of a level to pulse input converter, meaning it will only produce a single cycle pulse output each time when the input goes high, regardless of how long the input stay high. So this is due to the property of the edge detection circuit or edge triggered. So now we will compile it. Alright, and then we'll go to the simulation to see the output. And now we simulate it. Alright, so now you can see that because this is a active low input, so every time when the switch is at low, means it trigger at the edge here, and it goes only 1 cycle. So no matter how long the switch or the push button stay at low, or we trigger the push button as long as we want, but we only get 1 pulse output, which is 1 pulse cycle. Okay, now after we have done with this input filter, we'll go to the selector. The selector here we use a 3 4-bit bus multiplexer. So this is a 2-to-1 multiplexer but with a 4-bit. So we will choose, because we have 2 buttons, push button 1 will represent 2. So in binary 2 we connected here to VCC and ground, and push button 2 we will represent 5, so we will also connect it here, and then we put as the selector here. We can choose, so if the push button 1 is triggered, so it will choose 1, and the push button 2 not triggered, so we choose 0, so we get output 2, and same goes to 5. So now we will compile it. And now we will simulate it. so from here we can see when both push button is not pushed, so we will get 0. If push button 1 is pushed, we will get 2 in binary, so it's 0010, which is correct. If push button 2 is triggered, but push button 1 is not triggered, we will get 5, which is 0101 in binary, so which is also correct. If both push button is pushed, we will get 0 as well. So the output is what we expected. And now we'll look at the vending machine. Okay, here is our vending machine, and we connect two input filter to a respective push button here, and then we'll get the output. And then we use the prescaler. We have clock 1 and clock 2, where clock 2 is represent the high frequency, and clock 1 is only have low frequency, which is 1 Hz for the Night Rider here. And then we have a selector, so if we choose push button 1, we will get 2, okay, and if we choose let's say push button 2, we will get 5. So here we have a ripple carry adder, and then we have accumulator, and we accumulate every time we trigger the button, and then it will accumulate, and then it will send out the output, and one of the output will go back to the ripple carry adder to add up to sum up the next value. And then the accumulator will send out one of the output to the BCD converter. This is for the display to the 7-segment BCD decoder display, and the other output will send to the comparator. So if because the comparator here at the input B here is already assigned as 11, so if the output from the accumulator is greater than 11, it will generate output 1, which will enable the Night Rider, and our Night Rider will go for 1 cycle, and until done here, it will clear the accumulator. So the Night Rider will be stopped looping after the accumulator output is less than 11, and the Night Rider is not enabled. Okay. And for the pin assignment, we assign our pin accordingly, and then we program it using the USB blaster to our CBLD. Okay.